Now, once done with public and private IP addresses, we can go look at routing to the internet. Routing to the internet. Let me get my pen ready in color. Let's use black. All right, network address translation. It translates the IPv4 address to the public IPv4 addresses, typically enabled on the edge router connecting to the internet. It translates the internal private addresses to the public global IP addresses. I think I touched on this briefly. Between the private and the public, in between, there is what we call address translation, network address translation. Since private IP addresses are not routable over the internet, they will need to be translated to public. And that is how we are able to route over the internet. So in this specific example, you can see we have a network here. It's this router, which we call the edge router. That IP address from the network 10.0.0.0/8, it is converted to a public IP address. That can be any IP address which is not in the range of these three networks. So to route over the internet, we need address translation. We'll look at NAT in CCNA 2. There are basic configurations that can be done on a router so that you can enable it to translate addresses. Special use IPv4 addresses. All right, we have also, so we're continuing with looking at types of IP addresses that we have. We have talked about private, we have talked about public, we've talked about unicast, we've talked about broadcast. We now look at what we call a loopback address. It is an address commonly identified by 127.0.0.1, and it is used on a host to test if TCP/IP is operational. So what a loopback interface is, it is basically an address which is used by a device to direct traffic back to itself. So if this device 192.168.10.10, if it wants to send traffic to itself, the goal in sending traffic to itself, verifying if TCP/IP is operational, it sends a ping to the loopback interface. As you can see from the from the commands here, ping 127.0.0.1. So the network for loopback interfaces is 127.0.0.0/8. That is the network for loopback interface. Any address in that range is a loopback interface. And it is used by a device to send traffic, to forward traffic towards itself. And the goal in doing that is to see if the TCP/IP is operational. If you receive traffic, therefore it is operational. We have what we call link local addresses. They are commonly used by automatic private IP addressing, in short, APIPA, or self-assigned addresses, used by Windows clients to self-configure when no DHCP servers are available. So link local addresses, you can see the network 169.254.0.0/16. In that range, these are addresses which are assigned to a device if no IP address is assigned statically, manually, and no IP address is found dynamically. All right, let me just introduce DHCP, dynamic configuration of addresses, and dynamic configuration of IP addresses, and static, that is manual. If you want to configure an IP address on a device, what do? For PCs, I think you go to network configurations, network adapters, you change the adapter, you go to options, advanced options, you change the IPv4 address. You can do that on your PC. Packet tracer, you go to the command, you go to IP configuration tab, you can change the IP address. That is manual configuration of the IP address. There is a dynamic way of giving or assigning a device an IP address, and it uses the protocol that we call DHCP. All right. So it's either you give a device an IP address manually, where you manually configure that IP address, or the device is given or assigned an address dynamically. It can be from a pool on the router. The router can give addresses to devices on certain networks. If no address is assigned on a device statically, and you choose to assign it dynamically, and dynamically there is no pools configured on the router, for example, it means that device will not have a DHCP to get its address. Where will it get its address? It will get its address from a range of these addresses, which is called a PIPA. I think we'll do a basic configuration where we can show in Packet Tracer, you can select DHCP, and if there is no DHCP server, you can see there's an address that comes that pops up on your IP address as subnet mask. That address is called an APIPA address, and it is a self-assigned address. So we'll get there. Very important, the link local address. Legacy classiful addressing. Addresses, they have classes. All right? Addresses, they have classes, class A, B, C, D, E. Classiful addressing wasted many IPv4 addresses. Classiful address allocation was replaced with classless addressing, which ignores the rules of class A, B, C. All right, let's start with understanding class A, B, C, D, E. All right, class A. Class A, initially, it was a class designed to support very large networks. Very large networks. How do we know that? If you look at class A, all right, let's look at this pie chart. Class A, 50% of all the addresses. How many? 16,777,214 addresses. 16 million addresses, class A. If I go back a little bit, where are those numbers coming from? We said an IP address is a 32-bit number, which identifies a host in a network. That number, it is separated by the mask so that we have the host and the network portion. The host portion can be used to determine how many addresses we can get from that host portion. So for example, if I have a /24 network, it means I have 24 bits being used for the network portion, and I have 8 bits being used for the host portion. If I have 2 to the power of n, it gives me an idea of how many addresses I can have from the bits that I have on the host portion. So if I have 8 bits on the host portion, it means I have 2 to the power of 8 addresses that I can get. And 2 to the power of 8 is 256. So it means with 8 bits, I can get 256 addresses. Now with class A, if you look at class A, it means we have 16 bits. Why? Because Here you can see it's /8. /8 means I have 8 bits which are being used for the network. Therefore, I have 16 bits which are being used, not 16, 24, to make a total of 32. If I have a /8, it means I have 32 bits being used for host. And probably if I have 2 to the power of 32, let me see, I might be wrong, but I hope I'm not wrong. 2 to the power of 32, okay, I'm definitely wrong, because we don't have all the 32 bits. 24, I mean, not 32. 24 here. Yeah, that was wrong. Let me see, 2 to the power of 24. Let me calculate. All right, that's the right number. So I'm saying in class A, I have a /8. What a /8 means, it means I have 24 bits left for the host portion. And if I have 2 to the power of 24, I get 16,777,216, which is close to this number that is right here. -2, we'll get to understand where the -2 come in later on. So class A, it was used for networks which have large number of addresses, which needs a large number of hosts, which has a large number of hosts. 16 million, that's a lot. So networks which are very huge, they use class A addresses. We go to class B, these are moderately large size networks. This is class B. So I think class B, it has 2 to the power of 16, that is around 65,000 addresses. So 16 million, I use class A. If I have around 60,000, I use class B. If I have around 254, I use class C. Because class C, it has /24, which means it has 8 bits for the hosts, 2 to the power of 8, 256. Now class D and E, these were reserved classes. Class D, it was used for multi-class addresses, and class E, it was just an experimental block which was reserved, not sure for what use. So you can see from these classes, what I can get from these classes is, if I have a network, I have an organization, and my organization needs 1 million addresses. What that means is I can only use class A addresses. I cannot use class B, because class B, it has 65K. That is not enough. So if I have an organization which requires 1 million addresses, it will definitely mean my IP addresses will look like those in class A. If I have around 60,000, there is no need for me to go and buy addresses from class A. Logically, from that era, there was no need to do that, because it's probably expensive. You probably get 1 million addresses that you won't be using, because you only need to use 65K. So these are the classes originally, 5 classes that we have. However, because there were wastages in those classes, we now have what we call classless instead of classful, classless address allocation, which we only have A, B, C classes. We'll get to explain those addressing. Assignment of IP addresses. Right here we have organizations. Where do we get the IP addresses? Where are those numbers coming from? There are people, there are organizations which sit down and they say, Africa should get these addresses, Asia should get these addresses, America, these addresses, Europe, these addresses. So we have the IANA, Internet Assigned Number Authority, which manages and allocates those IP addresses. We also have regional internet registries. So from the IANA, this is the highest organization which manages and allocates. We have different regional internet registries. We have one in Africa, Afrinic. We have one in Asia, Ethnic, etc., etc., etc. So addresses come from IANA. they go down to the regional registries. From the regional registries, probably they'll get to our service providers. From the service provider, they will go to your organization. From your organization decides which device gets what address. So basically, this is sort of the hierarchy of where the addresses are coming from. IANA, that's the boss, that's the organization which allocates. Then it flows down to the regional internet registries. From there, we get to our ISPs, probably our tier ones. I think tier one is probably our biggest ISP right now. Tier ones, then our liquid, then it goes to our small service providers. Okay, our tier ones, our access providers, our service providers, our telcos, our economies, our net ones, then to your organization, then my PC is 192.168.10.10. Assignment of IP addresses, where do they come from? Network segmentation, broadcast domains and segmentation. Many protocols uses broadcasts, multicast, switches propagate broadcasts, only devices that stops broadcasts, routers do not propagate broadcasts. Each router interface connects to a broadcast domain. Right, broadcast domains and segmentation. Let's start with defining what we call a broadcast domain. I said every interface on a router, it should lead you to a network. So if we have an interface right here, it leads me to this network. An interface also leads me to a broadcast domain. A broadcast domain is a domain where if a broadcast is to be sent in that network, then every device in that broadcast domain will get and receive that message. So that is a broadcast domain. If I have another interface here, it will mean I have another broadcast domain. If a PC in this broadcast domain sends a broadcast, every PC in this broadcast domain gets the message. That is what a broadcast domain is. Right. The problem with having large broadcast domains, it's okay we have a broadcast domain, but there is a problem which comes with having a large broadcast domain. Let's say we have 1,000 devices in our broadcast domain. Gig, Ethernet, interface 00, we have 1,000 devices there. It means much of our protocols which uses broadcasts to function, when a broadcast is sent, it is sent to all 1,000 devices. It means probably these switches will process 1,000 frames. Every device in the network will process that frame as well. And that takes a toll on the network. Processing power of the network goes down. Why? Because it is dealing with all the broadcasts that are being sent in the network. So a large broadcast domain, okay, we have it, but it has problems. Problems comes when every device in that network probably is trying to send a broadcast. When we talk of ARP, for example, ARP, a PC wants to know a request is sent. I want to know what is my IP address, what is the MAC address, this is my IP address, what is my MAC address. It sends a broadcast automatically. Every device in the broadcast domain gets that. Even a device that should not be getting that ARP request, it gets that. Processing power of the network goes down. We have a problem. We have congestion in the network because every device is sending a broadcast. So that's why we have and need what we call segmentation. So instead of having 1,000 devices in one broadcast domain, we can have another interface here So instead of having 1000 here, I have 500 in this broadcast domain. I have 500 in this broadcast domain. I can as well add another interface. That is segmentation. Instead of having 500 here, I have 250. Or let's say I have 300. I have 300 here. And now here I have 400. So it means I'm reducing the number of traffic, reducing the number of devices in the broadcast domain, reducing the number of traffic. Therefore, probably we have less likely congestion, more traffic flow in a given broadcast domain. So segmentation is very important. In this example, we segmented by having different broadcast domains. And different broadcast domains means different interfaces. Different interfaces for every network. And that is what segmenting is. That is what will lead to what we call subnetting as well. We will get there, right? The only device that stops a broadcast is a router, right? If a broadcast is sent by PC1 in this broadcast domain, it will not get past this point. Why? Because once it gets past this point, it gets to another network, and a broadcast belongs to only one network. Let's say our broadcast here is 192.168.10.255. We've dealt with this one. That is the broadcast address. You see another network like this one. Probably its network IP address is 192.168.20.0/24. Because we have a .20 here and we have a .20 here, those are two different networks. So even if this broadcast gets to this side, it will not be able, it will be dropped because it is going to a different network. That is routing now. An address gives you an idea where you are going. This address is saying, I stay in Harare.10. That's the network. I stay in Harare. If I'm sending a message to everyone, I'm sending a message to everyone in Harare. That is what this .10 means. This .20 means I'm sending a message to people in Bulawayo. So if you send a message with the .10 to people in Bulawayo, they probably won't get that message. That is why the router is where all the broadcast stops. Because the broadcast ID, it shows it's sending to a network, to a specific network, and that is the network of the original packet. We'll get to understand that much better as we go. Routers do not propagate broadcasts. The reason why they do not propagate broadcasts is because if I have a .10, it means I send it to Harare. And if I want to propagate to .20, it means I'm sending to Bulawayo. You cannot send a packet with an address saying Harare to Bulawayo. That's why a router is where everything to do with the broadcast stops. Very important to understand. As we continue, CCNA2, CCNA3, this will be the foundation of everything that we do there. Problems with large broadcast domains. Problem with large broadcast domains is that these hosts can generate excessive broadcasts. We've talked about that. The solution is to reduce the size of the network to create smaller broadcast domains. So instead of having 400 users in one domain, you can have 200 and 200. Total is 400, but they are now in two different broadcast domains. Dividing the network into two subnets, broadcasts are only propagated within these smaller broadcast domains. So this is the solution. The problem is excessive broadcasts, excessive traffic, congestion, slow performance, slow networks. It's because of large broadcast domains. We segment, we divide, we get two different subnets, smaller broadcast domains. So instead of having 400, we now have 200. We will deal with consequences of this later on. The consequences of this is, if you look at the addressing, Here the address is 172.16.00/16. 400 addresses. But here we now have 172.16.0.0/24. Here we have 172.16.1.0/24. Two different networks. So instead of having, or I'm sending to everyone in Harare, I now have, I'm sending to people in Highfields and people in CBD. Two different areas, but still both are in Harare. So that is what segmenting a network is. Instead of sending to 400 people saying I'm sending to Harare people, I now divide. I say, okay, I'm sending to Highfields, I'm sending to Stungwiza, Harare, no. I'm sending to Kwazana, I'm sending to Upper Samora, etc., etc. Basically, that is what segmenting a network is. Reasons for segmenting a network: subnetting reduces network traffic, improves network performance. It can be used to implement security policies, reduces the number of devices affected by abnormal broadcast. Right. Number one, we've explained it. Overall network performance decreases. Why? Because we have more broadcast traffic. More processing power is now needed to process that traffic, meaning the network performance decreases, I mean. Right. It can be used to implement security policies. Let's say, in this example, security policies. How do I explain this? If I want to say people in Highfield should not get a network, it's very difficult to do it here. We have 400 users. Among these 400, we have people from Highfield and Guadzana. So we have people from Highfield and Guadzana. It's still Harare. If I want to say people from Highfield should not get the network, it's very difficult to do that because they're in the same network. It's possible, but a bit complex, right? But if I separate, if I say this is Highfield, this is Guadzana, I can easily say, shut down this interface, therefore people from Highfield will not get the network. So segmenting, it has that advantage. Security-wise, we have a threat, people in Highfields, there's a threat there. So shut down that network so that we shut down the threat. This is how we do it. But if you have a large broadcast domain, everyone is in that same network, it's very difficult to do that. That's why we have network segmentation. Another reason, reduces the number of devices affected by an abnormal broadcast traffic. Let's leave abnormal broadcast traffic. Let's say this link was an Harare. Let's say instead, we are not the one who shut down this link. Let's say this link, someone store cables there. This link is now not active. What it means is only people in Highfield will not get the network, but people in Kwazana will get the network. However, if they are all in the same broadcast domain, if this link goes down, everyone will be affected. So segmenting networks comes with a number of advantages. We've already talked performance. We've talked of implementation of security policies. We've talked of number of devices being affected if a network goes down. Subnets are used for a variety of reasons, including, okay, grouping by location. The example I was giving, I was grouping by location, Highfields, Kuwazana. So I was grouping devices by location. All devices in Highfields, they have a network on its own. All devices in Kuwazana, they have their own network. I was grouping by location. You can do that on a building as well. So you can see on this building, location, this building. Let's say this is the first floor, this is the second floor, third floor, fourth floor, fifth floor. They all have different networks. If network in the first floor goes down, 2, 3, 4, 5 will still function because they are not in the same network. That's the advantage of segmenting a network. They can be grouped in terms of groups of function. So I have people in admin, people in human resources, students, and I have accounting. All students, they have their network. In terms of security, it means students will not be able to, let's say, eavesdrop, see traffic, eavesdrop traffic from administration. Why? Because they are not in the same network. Students, they have their own network. Therefore, they cannot see traffic which is being used by the administration because they have different networks. Okay, if we go a little bit deep, they can. We have students who are able to see that. But let's just say in the simple world, they cannot because they have different networks. So we have grouped by functions. We can do that as well. We can group by device types. All devices, all end devices, your computers, your laptops, your phones, they are given their own network. All devices, all printers, they're given their network. All servers, they're given their networks. So you can see we have different ways we can segment a network. I started with segmenting by location. You can segment by function of a group of devices. If a group of devices is being used by students, therefore they have their own network. Admin network, sales network, electrical engineers network, network engineers, their own network, group of function, or as well as device type. Very important. Subnetting an IPv4 network. Right? I think I'm going to end here, 11.5. Then I will have another session because I think this is probably another 1 or 2 sessions, subnetting an IPv4 network. As for today, let's call it a class.